Hello, welcome to another module in this massive open online course. So, we are looking at convex sets. Let us continue our discussion by looking at another very important convex set, which is the ellipse or the ellipsoid. Alright, so we want to look at the ellipse, or also in n dimension, also an ellipsoid or an ellipsoidal region. Alright, and an ellipse, as you know from knowledge of your high school, it looks something like this, and is typically described by the equation. We are going to come to the general model in a little bit, but first look at a very simple equation for an ellipse described by the equation x square by a square plus y square by b square equals 1. So, this is an ellipse. Well, this is the equation of the ellipse, and the interior of the ellipse including the boundary is described by this inequality, that is x square by a square plus y square by b square equals 1. This describes the interior of the ellipse. Now, this can be simplified as follows. To get the general expression for an ellipse or an ellipsoidal region, I can write this as let us write this, or let us write this instead of y square by b square, let us write this as x1 square by a square plus x2 square by b square is less than or equal to 1. Okay, where x1 and x2, so x1 is denoting your conventional x coordinate and x2 is denoting your conventional y coordinate. Okay, and now I can write this as, so I can denote this by a vector x bar equals x1 and x2, x1 x2 two components. So, this will help me generalize it to n dimensions. So, this will be x1 x2 times 1 over a 0 1 over b. In fact, let me just write one more step. I can write this as 1 over a square 1 over b square times x1 x2 less than or equal to 1, writing this in vector and matrix notation. So, this implies we have x1 x2 times 1 over a 0 0 1 over b into the matrix itself, because it is a diagonal matrix. Matrix into itself will give me 1 over a square, or 1 over a square and 1 over b square. Okay, 1 over a 0 0 1 over b into x1 x2. Well, this is less than or equal to, this is less than or equal to 1. Okay, and this you can see now, this is basically nothing but transpose of the vector x bar. So, this is x bar transpose, this is the vector x bar, and you can see if I call this matrix as A inverse, remember I can define A as the matrix, diagonal matrix A, small a and B on the diagonal. So, this is A inverse, and I can write this as A inverse transpose, because this is a diagonal matrix, the matrix is equal to its transpose. So, A inverse and A inverse transpose. So, I can simplify this now interestingly as x bar transpose A inverse transpose into A inverse into x bar less than or equal to A inverse into x bar less than or equal to 1. Remember, this is our matrix A, that is a diagonal matrix with A and B on the diagonal, and this implies, and of course you can see that this implies A inverse equals simply 1 over A 0 0 1 over B. Okay. Now, the above inequality implies, now I can write this as follows, I can write this as A inverse x bar transpose into A inverse x bar less than or equal to 1, and now you can clearly see the vector transpose itself is nothing but the norm of the vector squares. That is, if u bar is a vector, we have already seen that u bar transpose u bar is basically norm u bar square. So, I can write this now very interestingly as norm A inverse x bar square less than or equal to 1, that implies A inverse x bar is norm of A inverse x bar is less than or equal to 1, and this is the equation of an ellipse. Equation of ellipse above, and now you can generalize this ellipsoid by considering an n dimensional vector. So, all right. So, you can generalize this in dimensions by considering an n dimensional vector x bar. So, if you consider instead of x1 x2, if you consider an n dimensional vector x1 x2 up to xn, norm A inverse x bar less than or equal to norm A inverse x bar less than or equal to 1, this becomes an ellipsoid, an n dimensional ellipsoid. Okay. Generalize this to n dimensionals. Okay. So, that becomes an ellipsoid, okay, in n dimensions. Okay. And now, the alternative representation of an ellipse or an ellipsoid now, the alternative representation similar to that of a norm ball can be derived as follows. Well, we have norm A inverse x bar is less than equal to 1 implies I can set A inverse x bar as a vector u bar with norm u bar less than equal to 1, that implies x bar equals A times u bar with norm u bar less than equal to 1. Now, this is for center as origin ellipse with, remember, this equation here we have started with, this is a center is origin. Okay. Now, if center is not the origin, then I can simply modify this to include the appropriate center as x bar equals A times u bar plus x bar c. So, this is the center of the ellipse or the ellipsoid. This is the center of the ellipsoidal region. Okay. And therefore, the ellipsoid can now be represented as the ellipsoid with corresponding to matrix A and center x c bar is the set of all vectors x bar x c bar plus a u bar such that norm of u bar is less than or equal to 1. This is the alternative representation of the ellipsoidal region. This is the alternative representation of the ellipsoidal region, all right. Ellipsoidal region corresponding to a matrix A and the center x bar C. Okay. Similar to the previous cases, let us look at a practical application of this. So, one of the aspects of this course is to also look at a practical applications of these concepts. Is to also look at a practical application. Okay. Again we will look at a multi antenna wireless system. Let us consider a multi antenna wireless system, again similar to what we have seen before. Remember, multi antenna wireless system basically has multiple antennas for improved performance of such systems. So, I have multiple antennas, and corresponding to these multiple antennas I have multiple channel coefficients H1, H2 to HL. So, these are the L antennas. So, these are, let us say, L antennas. So, this is your receiver in the wireless communication system. You have the L antennas. So, H1, H2, HL are the channel coefficients. Now, these channel coefficients also in wireless communication systems, the knowledge of these channel coefficients, this is also termed as channel state information, all right. So, the channel coefficients characterize the channel state, and knowledge of this channel, that is knowing these channel coefficients, having the values of these channel coefficients, is also termed as channel state information in the wireless communication system. So, the knowledge of these channel coefficients, this is also termed as, this is a frequent term, this is termed as channel state information. Okay. Knowledge of these channel coefficients is termed as channel state information. Now, this knowledge is important. Now, to develop enhanced signal processing scheme, we need knowledge of these channel coefficients, or we need the channel state information at the receiver to develop improved, or to basically develop schemes that yield improved performance after signal processing at the receiver. Okay. So, this knowledge of CSI is required for accurate improved performance. However, frequently the exact channel state information, that is frequently the exact channel state information is not known in this is not known in practice. Now, what is known, because remember these channel state coefficients have to be estimated, and whenever you estimate them there is going to be an estimation error. So, only approximate channel values of these channel state information or approximate values of these channel coefficients are known, that is the corresponding to the approximate values or the estimates of these channel coefficients are frequently known in practice. Okay. So, only the estimates, exact CSI is not known, only estimates or basically you can think of these also approximate values, only estimates of channel coefficients or CSI is known. This implies that there is uncertainty in the CSI, implies this is termed as uncertainty, CSI uncertainty. This uncertainty in the CSI arising from the estimation errors. There is uncertainty in the channel state information. So, we have these estimates. So, we have these true channel coefficients. The true underlying channel coefficients, these are not known, and what are known are the estimates that are denoted by these hats H1 hat, H2 hat up to HL hat. These are the estimates of the channel coefficients. Okay. And therefore, we have our true channel vector H bar, this is H1, H2 up to HL, okay, and this is your true channel vector meaning the actual channel vector in the wireless system, and you have the estimated channel vector H hat, which is equal to, comprises of the estimates and this is the true CSI, or what is also known as perfect CSI. This is the estimated channel coefficient vector, which is also known as this is the estimated channel vector. This is also termed as the imperfect CSI. Okay, this is all the, this is known as imperfect CSI. Now, we know that this imperfect CSI is close to the actual CSI, that is H hat, the estimate is close to H bar, but it is not exactly equal to H bar. Okay. So, H hat we know is approximately equal to H bar, but H hat is not exactly equal to H bar, and this is an important consideration in practice, because in practice the perfect channel state information is very difficult. I mean, estimating the underlying channel state coefficients without, that is with 100% accuracy, without any estimation error is impossible. Alright. So, in all practical scenarios the channel state information or the channel coefficients are only approximately known. Alright. So, one has to characterize this phenomenon of uncertainty in the CSI has to be suitably characterized to design signal processing schemes that take into account this uncertainty into CSI and yield improved performance. Okay. So, we have to have, so H hat is close to H bar, but H hat is not equal to H bar. So, how to characterize this uncertainty? How do we characterize? The important question now is how to characterize this uncertainty, and therefore, what one can say is that h hat, this estimate, lies close to h bar or h bar, the true channel, lies close to the estimate h hat. We can say that h bar lies in a region of uncertainty around h hat, and this region is frequently modeled as an ellipsoid. Okay. So, what we have, and this is where the application of the ellipsoid comes in, we say that if you consider an ellipsoidal region with the known estimate as the center, then h bar, the true channel, lies in a region, uncertainty region. So, h bar equals the true channel. It lies in a region of uncertainty around h hat, which is the estimate. Okay, and this uncertainty region typically modeled. So, this is an uncertainty region. This is typically modeled as an ellipsoid in n dimensions. This is typically modeled as an this uncertainty region is typically modeled as an ellipsoid. So, we say that a true channel vector, true channel, lies in an ellipsoid. Lies somewhere in an ellipsoid around h hat. Now, obviously, if the ellipsoid is large, that means the uncertainty region is large, which means the estimation error is high. Alright. Now, if the estimation error is low, that is the estimation process is very good, then the ellipsoid will suitably small. That is, you can localize h bar to a much smaller region around h hat. So, if estimation is accurate, that implies ellipsoid, that is the size of ellipse is small. Okay. On the other hand, inaccurate estimation or poor estimation, the estimation poor implies ellipsoid is large. So, one can characterize the ellipsoid based on the estimation process also. Okay, because the estimation process what results in the estimation errors. If the estimation error is large, then the uncertainty will be large, the size of the ellipsoid will be large, that is there is a lot of uncertainty in where h bar can lie. If the estimation is of good quality, then naturally h bar will be close to h hat. So, the size of the ellipsoid will be much smaller, and asymptotically you can see when the estimation error becomes 0, h bar, the true channel, coincides with h hat. That is for a large number of pilot symbols, that is when the SNR of estimation tends towards infinity. Okay. Alright, and therefore, now you have an interesting model to characterize the true channel vector. I can represent h bar as a times u bar plus, remember this ellipsoid has center E, which is nothing but h hat. So, this forms your center of the ellipsoid. H hat is center of the uncertainty ellipsoid. So, h form, so h hat is nothing but the center of the uncertainty ellipsoid. Okay. And therefore, h bar belongs to this uncertainty ellipsoid, which is given as a u bar plus h hat such that norm u bar is less than or equal to 1. Okay. And this is termed as I already said, this is termed as the uncertainty ellipsoid. This is termed as, for this practical scenario, this is termed as the uncertainty ellipsoid. This is termed as the uncertainty ellipsoid. And now signal processing techniques that concern this, that consider this uncertainty, signal processing ellipsoids that consider uncertainty are termed as robust. These are termed as robust since they are not sensitive to the uncertainty in the channel state information, as they are not sensitive or less sensitive, as they are less sensitive to uncertainty in the channel state information, okay, or they are not sensitive to errors, not sensitive to estimation errors. As they are not sensitive to estimation error. Alright. So, an interesting application of this ellipsoid or ellipsoidal region in wireless communication, or for that matter signal processing and various other applications, is the following. Several quantities have to be estimated, such as the channel coefficients, or even in signal processing, alright, an underlying filter has to be estimated, alright. So, the true coefficients, we do not know where what the true coefficients are, but we know that they lie close to the estimated values. So, these can be considered to lie in an ellipsoidal region around their corresponding, around their respective estimated values, alright, and that ellipsoidal region is known as the uncertainty ellipsoid. In the context of wireless communication, this arises because there is uncertainty in the CSI, channel state information, or the channel coefficients, alright. So, let us stop here and consider other aspects in the subsequent modules. Thank you very much.